joining, almost 70 plus joined.
Okay, okay. Okay, thank you very much, Dr. Srinivas.
Thank you.
So, dear participants, this is the slide at which we had stopped and we took a small break. Let me go back 2-3 slides back where we were discussing some interesting phenomena about the radiative transfer equation, because this is what I am going to talk about. And my objective is to correlate it with the material property, which is in the equation over here. So this is the optical property of any material, which is given as n plus I kappa. So there is a real component to the refractive index and the imaginary component to the refractive index. And I gave already some examples for different materials, starting with vacuum. Then we have the case which will come for clouds, because it is made of water droplets, air, because this is what leads to that blue color of the sky as well as the red color of the sky in the evening. And then tissue, aluminum, copper, dye, any material, we can measure these optical properties. And then I discussed the actual optical properties for water, and how very interesting in nature that the wavelength in which the solar irradiation is maximum because sun, it emits at, so what that question I will also answer, that it's kind of a black body which emits at this particular wavelength. So this particular temperature is the effective black body temperature. So these are the range of wavelength in which the intensity peaks, and it so happens that all our human eyes are maximum sensitive in this region, and as well as water, which covers 70% of the surface of the earth, and it is having the lowest absorption coefficient. So this imaginary component K is the absorption coefficient in this range. So we'll make use of this particular property. We will look at how sunlight travels through atmosphere, what happens to it, and I will correlate it with the reduction in pollution which took place during the lockdown period, which allowed the residents of very far off places like Jalandhar to view the beauty of the snow-capped Himalayan peaks. And we will correlate the white color of the clouds over here. These are the cloud, and the blue color of the background sky. And why does that sky turn reddish color? Because of the color of the sun in the sunset and during the sunrise. And those things we will be able to correlate with the help of the radiative transport equation. So let us go ahead. After the break, we have rejoined, and we will look at the radiative transfer equation, whose simplified form looks like this differential equation over here. And if you remember your mathematical background over here, if it is a simple term, then the answer will turn out to be some sort of an exponential decay over here with some coefficient which will appear before x. So we will figure out how do we actually solve it, and what are these three subscripts which are written over here. So Ka is stand for the absorption coefficient, S stands for the scattering coefficient, and if we add them together, A plus S, we get E, which is the total extinction coefficient, which is the sum of the absorption caused by a material and scattering caused by a material. Then we will be able to answer questions like what exactly is scattering and what causes light to scatter, and do even matter scatter, like nuclei and atoms and particles. And I didn't want to look at the full version, so just as a comprehension I have shown over here that the simplified form just contains the first two terms of the full version. So in this particular lecture, I won't go into the full version, but those participants who are interested and having the background in heat transfer themselves, if they want, they can look at any standard textbook, like I have been following the modest book, Heat Transfer, and it gives very interesting result. So scattering, if we look at it, is a generic term which consists of various individual phenomena that we are all familiar with. Reflection, everybody knows. Refraction, everybody knows. So we have studied in high school physics itself. So if there is, let's say, a mirror surface over here, and this is the line along which light is propagating. So this is the incident, and I can call it theta I. So we know from the first law of reflection that light will reflect from this reflective surface, and this angle theta r. So theta I is equals to theta r. This is the first law of reflection. And we also know about refraction, which is something when light travels one medium to another medium. So we all remember this, again we have studied in high school, that if light goes from air to glass, so this line represents an interface where the medium is changing from air to glass. So it doesn't continue to go in the same line of propagation. It actually bends towards over here. And the reason for that is that the refractive index of glass, if I remember correctly, it's probably 1.5. It is much higher than the refractive index of air, which is very close to 1. So over here we have, this is theta1, this is theta2. So you all remember Snell's law, n1 sine theta 1 is equals to n2 sine theta 2. And then more complicated phenomena like diffraction may also take place. So sum of all these phenomena is termed as scattering. So scattering is a blanket term which envelopes a lot of individual phenomena, but all of them are dealing with the wave. And in our particular case, it is the electromagnetic wave that we are looking at. So I think I have some animation and some figures over here which kind of give an analogy of scattering. So if you see in this billiard table over here, the cue ball hits these set of stationary balls, and one may say, figuratively speaking, that all these balls are scattered in different directions. And if you remember again from our high school science, that all the phenomena of the rainbow which is formed, so if people have to answer it, then historically there are a lot of other explanations which are given, but in reality it is formed due to the presence of raindrops or the particles in the atmosphere, especially during when it is raining. So sunlight passes through it and then scattering takes place, and we form this kind of a rainbow. And this is the classical Rutherford experiment, where he observed, then he bombarded this particular material, thin material over here, with nuclei, then with, I think, alpha particles over here. Then huge amount of scattering would take place for some particles. So even historical precedence is there, and even the structure of the atom with a very small nucleus, electron around it, is actually explained very well by this Rutherford scattering experiment. So these are just some background behind it. So I wanted to give an example of scattering of light by a medium. So one example is if we have, let's say, a circular body or a spherical body. So let me go ahead and draw it over here. So let us say if we have a droplet of water, or let us say a sphere of glass, which is not very small size. So we're not talking about nanoparticles right now. It could be of the order of diameter, could be 1 millimeter. And let's try and see what happens when light passes through over here. So if light is going through this particular axis, then what will happen? Most of it, because water is transparent, of course, so this is a water droplet, and all around it, it is surrounded with air. And let us say green light is going through over here. So by green light, we know the wavelength is about 0.5 micron. So this is a category of electromagnetic wave. Because we can see it, we also term it as light. So this light wave which is passing through over here it will see an interface. So at this point over here, it will notice there is an interface air and water. But because it is normally incident over here, small portion of it will be reflected back. Majority of this intensity will continue traveling in the straight line over here. Then it will see a second interface over here. Then again some small portion will get reflected, but majority of it goes in the straight direction. So it's a very simple phenomena. I may put some numbers over here. If let's say 1000 watts per meter square is incident over here, maybe about 5%, or let's say 50 watt per meter square gets reflected. And over here we have remaining 950 watt. Then again another 50 watt reflected, or maybe I'll change this number. Let me put 40 watts over here. Then what comes out over here is 910 watts per meter square. So simply by reflection, some part of this light is actually lost, and where it is going, this is being reflected back in this direction. The light which is reflected from the secondary interface, it will continue to bounce, some portion will come back over here, and then multiple reflections. So this is the simplest case, and we don't see any evidence of scattering taking place over here right now. But let us see if this light was incident at some particular offset. So it will not go now through the center of this particular water droplet, but rather will go in this direction. It will continue and hit this particular point. And at that point, it is again seeing an interface between air and water, but this time that interface makes a particular angle. So we can clearly see this is the angle over here. So I'll write it over here, let's say theta1. And instead of continuing in the same direction, because refraction mandates that when it goes from a lighter medium to a denser medium, it should bend towards it. So it bends a little bit over here. Is it clear up till this point? And then it continues to travel. I'm not making a line. In reality, it will be straight, but my stylus is moving a little bit funny. So over here again, it will encounter a particular interface. And at that interface, one more reflection will take place over here. So this is the internal reflection which is taking place. In the first case also, small reflection took place. Then it went in that direction. Then what happens to this particular light? Will it continue to travel in this particular direction, or will it bend outward? So then it goes from denser to rarer medium, so it will bend outwards over here. So majority of the light, let us say again, I'll give the same number, 1000 watts per meter square. Little bit less is reflected over here. Then about 950 is coming out over here. Then little bit less is again reflected over here, maybe again 910. Sorry, 40 over here. And then we have 910 watts per meter square coming out. So you clearly see there is a change in direction over here. And in addition to this 910, there is one which is coming out from over here. And this thing will keep on happening at multiple times. Instead of going over there, it will bend in this direction, remaining will go over here, and so on and so forth. So it will go over there, some part here, and some part there, some part reflected. So if I can then show with the red color that this is the main, this is the main direction in which it will go. And you have clearly seen that this shows that the light has actually bent. And there are other directions in which it will also go. And in reality, this law of Snell's, which says n1 sine theta 1 equals to n2 sine theta 2, there is a wavelength dependence over there as well, which means all of these quantities are actually dependent on wavelength. Which means inside over here itself, this droplet may even act like a prism. Why? Because a different color light, if we start from violet, indigo, blue, then green, then red. So the blue component and the red component will have different n values, which means the extent by which they are bent, the extent by which that angle deviation takes place is also very different. And when this happened multiple times, so this light which was coming over here, and this I'm talking about a transparent water droplet, because water is very, very transparent. Can I say water is transparent with full authority or full confidence? I can do so by going back to this particular slide over here. The table where we had shown the properties of water, it clearly shows, because this K represents absorption. When something is not being absorbed, it is actually being transmitted. So because the absorption coefficient is so small, everything is actually transparent. So believe it or not, each droplet inside this particular cloud is completely made of transparent water. And it is so small, very, very small. It's just like this particular glass which has just shattered. So this is kind of an example of a shatterproof glass, maybe in our windshield of the car. So this glass clearly is transparent to our naked eye. But when this kind of a shatter takes place, it completely turns white. And it becomes kind of opaque also, which means there could be an object hidden behind it. And that is one of the challenges for this cloud also. There could be objects which are hidden behind the cloud, and we are not able to penetrate that particular wavelength through this. Why? Because light is being scattered. So sunlight hits the cloud over here, and then it gets scattered in all the direction. Because these droplets are fully transparent, absorption is very, very low. Cloud by themselves doesn't absorb sunlight very much, maybe just 1% or less than 1% even. But what happens to this 1,000 watts per meter square, which was coming from the sun? It gets distributed. Maybe 50 watt goes over there, 50 watt goes there, 50 there, 50 there. It may not be uniform. There may be some preference in the forward direction. On the sides, it may be low, 30 over there and 30 over there. But what it does is, to the ray optics, it totally confuses the direction. It goes in all the directions over there. And that is exactly what we see in north part of India during the fog time. So then it makes it very, very difficult for the train, flight, and even road operations to take place, because no matter how powerful your headlight is, or no matter how powerful is the light coming from the other direction. So if I'm, let's say, driving a train in this direction, I want to see what is the signal color 1 kilometer ahead. It is red or green. So that light has to enter our eye. Only then we are able to see whether it is there or not. But then it is going in all the directions. Very difficult to even understand what color is occurring over there. So this is the interesting phenomena of scattering, which gives the white color to the cloud over there, just as it has given the white color to this transparent glass over there. So it can be explained with this very simple phenomena of tracing the ray optics in this particular direction. And remember, this is just for one droplet. And then the same phenomena may take place for 500,000 or millions of droplets, suspended droplets in the cloud. So this information which was coming from over here, it is not able to reach on the other side over here. Where it goes, it just scatters in all the directions. So we just see that there is a bright color to the cloud. Cloud is not dark, it is light. But what is the information which is coming from this direction? It is not able to reach the detector. So this is one set of results that we have seen for the scattering part. The other set which I wanted to explain was that in addition to scattering, absorption is also taking place, because scattering was the second term over here. Absorption is the first term. Both are having the minus sign, which means both lead to the reduction in intensity. Both lead to reduction in intensity. So if I'm plotting intensity on the y-axis, as we travel along in the x-axis, intensity is continuously reducing. Now, is this phenomena also visible for, we have looked for the scattering part for the example of cloud and the shattered glass, but what about the absorption part? So the answer is yes. Even for that one, very interesting thing we see is that the scattering, and one more thing I want to tell is, scattering is a function of wavelength. So because of the presence of the molecules in the atmosphere, they scatter blue light much more than the red light. So blue light is scattered more. That is why all this atmosphere over here, that is appearing as blue. And during the evening time, when the sunset, at that time, sunlight has to travel through very long distance over there. Then again, major scattering and absorption takes place inside the atmosphere, and blue is the one which is predominantly absorbed and scattered. Then what is remaining is the red color. So during the sunsets, we are able to see the sun having the beautiful red color, orange color in the evening and in the morning. So these are all phenomena which are explained with one or two very simple equations which are shown over here, and they have impact on the solar, the study of solar energy, the study of traveling of light or the radiative transfer, which is taking place through space. So I thought I'll share this extra information. So I hope this point is clear. If there is any doubt, we can take it during the end when we are looking at the question answer. So we were looking at different applications. You remember we looked at solar drying, we looked at solar even travel using the car, aircraft, and the solar balloon. These are futuristic imaginations. Then we look at the terrestrial region. What exactly is happening right now using the solar energy? First, of course, is the solar collectors. We will look at that in details. And in addition to the simple solar collector, which heat up water for the household applications, we can also have the concentrating collectors. So these are looking at now applications. And you can see over here that there can be parabolic trough collectors. This is one type of collector, and you can imagine the scale by looking at the photograph of these humans over here. And they are able to achieve very high temperatures, maybe around 150, 200 degrees centigrade. But if we want to achieve even significantly higher temperature compared to that, then the concept of the central tower or the power tower has to be used, where the central tower is located here in the middle, and all these heliostats, these are essentially mirrors which track the in such a way that the sunlight which is reflected back from each of this mirror, it hits the particular point on the tower. It heats it up so much because you can imagine there is thousands of these mirrors all across. So the temperature at the tower becomes very, very high. So, and then there are other configurations also. In each one of them, there are or three common things. One is that in all of them, tracking mechanism is needed, which means in the case of parabolic trough collector, this parabolic trough collector needs to track the sun, because relative to it, sun will be moving during the day from east to west. The same thing happening in solar tower. So all these heliostats, even the dish, and even the linear Fresnel concentrator, they need to have a tracking mechanism. The second and important thing, so that is the collection part over there. They need to concentrate all the solar energy through these type of geometries. So it could be a parabolic geometry, it could be a line geometry, it could be a central tower geometry. Then the important thing which comes next is the medium, whether it is gas or steam, some sort of oil or molten salt, some sort of fluid is needed to transport thermal energy from point A to point B. And point A is generally the center of the dish over here. And point B could be, if you are looking at electricity generation, it could be the turbine. So we need that heat which is collected through the dish to be transferred from one point to another. And the reason is that there are very long tubes in which this fluid has to flow. And maybe the turbine is located at this central location over here. So all the heat which is captured by each and every one of these pipes has to transport that heat to that particular turbine, force the turbine to run, and that can be done by a particular fluid which can sustain high temperatures. And in this whole process, you can clearly see heat transfer plays a very, very significant role. And the most important characteristic that we have to look at is the efficiency of the system. So now I will enter the technical part of this particular talk, and where we will start that talk by asking a very fundamental questions, that what is the technology that we can use to absorb sunlight? Like one gentleman had asked one question earlier, that black body is something which is having the perfect absorption, then how can it emit? So we will look at that question in the context of nanoparticles also. That what absorption characteristic is there of nanoparticle, and do they emit also? In order to understand that, I think first we have to go and look at little bit background of the nanotechnology, that these nanoparticles which are a very, very small, and do we find them all around us? So today the answer is yes. Even in the normal daily life, lot of material is actually built up using the nanoparticles, including the sunscreen, including the nanocomposite coatings, and including even some of the advanced solar photovoltaic panels. You might have heard names of graphene and carbon nanotubes, for which a lot of research is taking place right now, including in our lab. So let us look at what exactly is nanotechnology. So the formal definition of nanotechnology is, it is the science, engineering, and technology which is conducted at the nanoscale, which is defined as any one dimension of a particular object should have at least one dimension between the range 1 nanometer and 100 nanometer. So let us start off with something that we can observe with our human eye. If we look at the human hair, the length could be very long, maybe 1 or 2 centimeter, or even 12 inches or so. But the thickness of that particular human hair is of the order of micron. It could be 10 micron, 50 micron. So we can't call a hair as a nanoparticle. If we look at our blood composition, so the red blood cell are slightly smaller in that. Then we look at visible light. Then we are looking at the 400 to 700 nanometer. Then bacteria is much less. And then today we are looking at virus, and everywhere that COVID virus, coronavirus, that thing is. So then we are starting to appear in the nanometer range. So in this particular range, nanometer range, 1 nanometer to 100 nanometer, and of course there are things which are much smaller than that. DNA and antibodies are even much smaller than that, and of course atoms are of the order of angstrom level, so zero point 0.1 nanometer and so on. Why is nanoparticle important, and what is the historical significance of nanoparticles? So let us try and see, have nanoparticles only been used recently in the last 20 years, or there is some example from much earlier? So I think this shows the example of stained glass window. So these are images of colorful designs that we can see. So these were present in ancient buildings which were built in Europe and many other places, where to give very beautiful depiction, so some colored glass is used, and the technical name of that is the stained glass. So glass is mostly which is used in window is transparent. So one way of making it colored is to put some paint on top of it. So you can take a transparent glass, put some red watercolor. Advantage with that is that color will fade off in maybe 5 year or 10 year, or somebody wipes it off. So these stained glass don't have any color coating on them. It is the color of the inherent material itself, and this goes back, historical records show, to about 6th century. And when people have looked inside them, so to in the SEM and the latest microscopes, they have actually found that there is color, there are nanoparticle which are present inside this glass structure. Of course, at that particular time, those technicians, artisans did not have any idea of nanoparticle. They were just using some technology, some technique which they had learned through hit and trial. That when they are melting the glass and then solidifying it again, if you add some impurities, maybe little bit of copper, little iron, little nitrate, and other things, so they would see that resulting glass would have very beautiful color inside. So it was kind of hit and trial process. During at that time, advanced science was not actually well known. So this is a very good example of something which is actually being practically used even without knowing the theory behind it. So that brings us to a question from our daily life. If somebody asks that, okay, we are talking about the color of these stained glass windows, let us look at some very common objects like gold and silver. So somebody asks, what is the color of gold and silver at macro scale, at the scale that we see them, maybe in a ring or a small gold coin, similar with the silver also gold. So we know the color is very, very conveniently known, that the gold is having yellowish color, or even some people call the golden color, and silver is highly reflective, whitish kind of color, and known as the silver paint also. But if we ask that question at a different scale, let us say if we ask that question at micro scale, that if we have not having this long gold bar, maybe of 1 centimeter or 2 centimeter long, but maybe if it is of the order of nanometer or micrometer scale, then color should remain same, isn't it? But it doesn't remain the same. It becomes very, very interesting. So this slide has been taken, the reference is shown over here, Northwestern University, where they have experimentally shown that at very small size, so you just see the size is of the order of 100 nanometer, sometimes it's 50 nanometer, 80 nanometer, 40 nanometer, and these are mixtures. So some cases are silver, some cases are gold. Okay, that is clearly mentioned, but the interesting things are the resulting color. Can we imagine gold having the green color or silver having the red color? But these are experimental results, actual results. So it's, our conclusion is that yes, at smaller scale we can play around with the properties of material, which is not possible at bulk scale. I can't change the color, expect the color of gold to change when I make it from 1 centimeter to 1 meter. If let's say I'm a very rich person, I am able to get 1 meter long rod of gold, I would still expect it to have the same color as the 1 centimeter portion had. Then what is so special at small scales? So one answer for that is, if we take a water droplet, and we try to make it small water, split it into small water droplet, what is the difference between these two? This I'll call it case A and this is case B. Even though the total mass may be same, this could be 10 gram and addition of all them together is 10 gram. Chemically, what is the difference between them? Composition is exactly same. If this is H2O droplet, this is also H2O droplet. But from an electronic point of view and from the electron point of view, has something changed? And the same thing would happen for copper as well. If I have a copper block over here and I split it into small copper blocks having the exact same mass, which means if this whole thing was 1 gram, all of these copper blocks put together is 1 gram. And you know, in copper block, electron plays a very important role because copper is one of the very best electrical conductors. So it so happens that the only thing which is changed from the bulk form to the small form, chemical composition doesn't change, but the number density of the surface electron totally changes. Why is that? Because if the surface area of this particular droplet was, let's say, A, the surface area of these droplets is going to be much higher than that. It could be even 100 times A or 1,000 times or even a million times, depending on how small I make these droplets. And the number of surface electrons over here will be 100 times less compared to the surface electrons over there. I think this point is clear. So what has surface electron got to do with anything optical property, chemical property, or electrical property? The answer is everything. So all these properties that we measure for a particular material is directly a function of how many electrons can transport from that particular point. So these three properties are directly correlated with one another: optical constants, electrical constant, and the chemical constant, because they actually provide the interaction of that material with the surroundings. And that is the exact reason why gold and silver at very small scale, they behave differently. Their coefficients actually change completely. So their absorption coefficient may no longer remain that there earlier. What are the other things which give us color in our daily life? So we were talking about colors of that gold and silver nanoparticles. If I want to make green color, why do I have to buy gold and make it small? I think we have all had experience of using some natural dye or chemical dye, maybe during the watercolor activity or maybe during some festival, we use some dye colors to mark it. And then these are made chemically through some extracts and some chemical process are there. But at the end of the day, all of them, they have some chemicals inside them which are chemically classified as dyes. And if there are chemistry people in the audience, they know that dye by definition, they have some optical property, which means they give out some color. And do they exist in nature before we started making them ourselves? So one example that I will give is the most commonly known dye in the nature is the green color dye, which is present in all the leaves and known as the chlorophyll. So this we have studied in school level biology, and this is a very complex organic molecule over here. And my chemistry is not so strong. I can't name it the whole, I can't provide the name, but I can just provide the image over there. And it is such nice function of this chlorophyll. It will absorb the photons which are emitted by the sun, absorb it and help in during the photosynthesis process. So this is something which we have learned in biology class. And if now we start looking at it from an engineering point of view, if I want the have the absorbance coefficient of this chlorophyll as a function of different wavelength light. So what we see very interesting is, of course, we go into detail, there are chlorophyll A, B, and many other types. But what we see is that there is very good absorbance in this range over here from 400 to 500. Then in the green range, which corresponds to this, then absorbance is very low, which means it is highly reflective in this particular region. And if green light it is reflecting, that is the reason why we are able to see the green color when we are looking at the leaf. So this part I wanted to correlate it with the different colors created by nanoparticles. Why? Because we want to put them in the context of solar energy. Now I'm putting that particular framework where I'm trying to ask a question. Is there a way I can use nanoparticles which exhibit different colors, which means they clearly show that the optical property is size dependent? Can I use that to selectively absorb certain portions of sunlight, which is what I want in my solar thermal collector? So as is shown in the figure over here very nicely, that between 400 and around 700 nanometer, so these wavelengths correspond to these particular colors, and a shorter wavelength correspond to ultraviolet, and much higher to this correspond to the infrared over there. So just in the visible spectrum, we can see that sunlight is emitting almost 50% of all its energy just between this small wavelength range. Remember, this is a very thin range, zero point 0.4 microns to about zero point 0.7 microns. So this is extremely thin if we compare the whole spectrum. The full spectrum is from, let's say, 0 micron to about several kilometer length, which is the radio wave and other very long wavelength. So that is the concept that we want to explore, but we want to also highlight there are some difficulties. The difficulty is if we use a natural dye, just like chlorophyll or any other organic based dyes. So even these colors that I was talking about over here, so these are organic dyes. So whatever uh, clothes that we wear, if let us say one day I am wearing a cloth which is having red color, I am wearing a red t-shirt or a green or a blue t-shirt, chances are that it is made of cotton. And cotton, you know, is white in color, just like the background of this particular paper over here. But I can always dye a white color material like cotton in red color, blue color, so that I can get some exciting. But those dyes, if themselves are made of these organic compounds, which I had shown over here, organic I am not very strong in, but one thing I do remember are that carbon molecules, they come together and form these long chains. And you have different kind of a bond, single bond and some double bond over here, and then single bond over here, something like this. Now, these bonds, because these are organic bonds, you may remember from chemistry, there is the sp2, sp3 hybridization. They are relatively weak when we compare to other type of bonds in nature. And what are the other bonds? Which is present in the crystalline solid. So if you look at copper, if you look at aluminum, if you look at gold, all those things, molecules are also having bond between one and another. But it's very difficult to break those particular bonds. And the exceptional case is, of course, diamond. Diamond is also made of carbon, but there is no way, because diamond is the hardest material in the world, very difficult to break that bond. But look at this particular die. Over here in this slide, it is shown in two portions. The bottom portion shows some 6 color different dyes. I can indicate them over here with a check mark over here. These are the different ones. And if we expose it to sunlight, let us say in this study it is done for about 20 months, then what do we observe over here? And what do we see is clearly some fading of the color takes place. And this is a phenomena which is not difficult to understand, because in our daily life, we observe any new cloth that we purchase after 2, 3, 5 years, the color inside it get faded. In fact, the interesting thing is the inner surface of that shirt, which is not exposed to sunlight, will continue to have original color. The outer surface will have a faded color, and it is all because of the action of sunlight, mainly the UV component of sunlight, which goes ahead and breaks these bonds that I was talking about earlier. So UV is the one which is responsible for breaking those weak organic bonds. What it tells us is, if I want to use these watercolor type of dyes for absorbing sunlight, it will be very difficult to do after few weeks or few months, because initially all these colors will be appearing very, very bright. But if I want to use it in a solar collector for absorption of sunlight, I have to use some inorganic technology. And that is why we want to address it, that can we use these type of nanoparticle material, add it to a base fluid which is shown over here. So in our research group, what we have done is we have tried to add aluminum nanoparticles over here. So if you go from A, B, C, D, E to F, You are adding more and more nanoparticles as a volume fraction, or a concentration you are increasing. So if I plot concentration over here, it is increasing in this direction. So as we go from A to B to C, our concentration is actually increasing. And clearly, it is becoming much more conducive for absorbing light, because anything which is black, it means that in the visible spectrum, it is not allowing any light to come out of here. If it was pure water like this, then light would enter here, it will come out from here. And these are some examples of some pure base fluid like silicon oil, ethylene glycol, water, paraffin oil, which are mostly transparent in the visible spectrum. So our main focus will be on the visible spectrum, which is zero point 0.4 to zero point 0.7 microns. And why it is the visible spectrum we are focusing? Because almost 50% of sunlight is incident in this region itself. So let us now look at this nanoparticle and base fluid combination together, and can we use it as an absorbing medium in sunlight? So next few slides will be related to that, and from this slide onward I will start presenting the technical details of the experimental and theoretical work we have done in our lab. So some very basic idea about a solar collector. If somebody asks what is the fundamentals of solar collector, any black surface that is put in the sunlight acts like a solar collector. The only thing is its efficiency is very low. So even if I put my scooter under sunlight, which is having the black color seat on that, and during summer that temperature can rise very much, 70, 80, 90 degrees centigrade. So essentially it is behaving like a absorber. So the same principle, we can put some insulation on top, that glass cover on top, insulation on bottom, so that that black surface is not losing heat as rapidly as would an exposed surface lose. So when it is losing heat rapidly, its temperature rise will be much less compared to if I'm able to trap that heat. And I can do it both for water configuration, also for the air configuration. So similar configuration is there. So that's all there is to it behind the solar collector configuration. Now comes the interesting part, and we will start looking at the wavelength dependence, which is very important. So if we look at the spatial optical property breakdown, I can put some numbers over here. So this is 3 microns. So predominant amount of sunlight is between 0 micron and 3 micron. So that is what is in red. It is given as the solar spectrum over here. And people who have already studied radiative heat transfer, they know that when the solar collector temperature will be maybe about 500 degrees centigrade, or let's say less, 200 degrees centigrade, I can convert it into kelvins, and it will be about, let's say, 600 Kelvin approximately. So if my sun, which was at the sun for our planet Earth, which is about 6000 Kelvin, and its peak wavelength is 0.5 micron, so you take the product of this, you will get 3000. So the same product we should get over here. This, what I'm telling is in short, the Wien's displacement law. So if my solar collector is operating at 600 Kelvin, which is 10 times less the temperature of the sun, so the peak wavelength will be 10 times more than the wavelength of the sun. So this is a rule of thumb over here. So essentially, our solar collector may emit at 5 micron or probably at even higher wavelengths. What it means is that we have very good split between the incoming solar spectrum and the outgoing emission spectrum. Because anything in this world which is having a certain temperature, it has to emit thermal wavelength. And that, if there are no overlap between it, or the overlap is very less, then we can use the technical term called the solar selective surface. So this I'm showing over here, this black curve over here. It has a very high absorptivity in the first part, short wavelength part. Then immediately at the cutoff wavelength, its absorptivity becomes very, very low. So I think they are not plotting absorptivity over here. What they are plotting is reflectivity, which is the inverse of absorptivity. So something which is having very low reflectivity, which means it is highly absorbing. Like if I put a black color surface and shine light on it, it is not reflecting anything, which means it's absorbing everything. On the other hand, if I have a mirror finish some sort of a polished aluminum surface, it is going to reflect everything for the same reason that it's not absorbing anything. So this is the concept of the solar selective surface, which needs to be created, needs to be designed by using different chemicals, and lot of uh, detailed study has to be carried out over there. But the principle remains very, very clear. I think this part is clear to all the participants, that there is a clear distinction between the short wavelength and the long wavelength. And what as the engineers we are going to do is exploit this difference in the wavelength, because the first part we can treat in a different category, and the second part we will treat in a different category. Okay. Now we come to the concept of this direct absorption solar collector, because we are able to understand that the presence of these nanoparticles can be treated as absorbing medium, and what we can do is create an improvement on top of the conventional solar collectors. So this is the proposal, or this is the idea. And the idea genesis is because in a conventional solar collector, there is always a collector surface on the top. So I'll show it over here. It is shown in red color, but usually this absorber plate is having a black coating. So this is that black surface which is uh, absorbing the sunlight directly incident upon it. It gets very, very hot, and then because of its high temperature, it is able to convect and conduct heat to the fluid which is flowing below it. So this is the general working principle of any solar collector which is conventionally available in the market as of today. So there is a fluid which enters at low temperature. Let us say it comes at 30 degrees. And then because of the high temperature surface on the top, maybe the surface temperature can go as high as 95 degrees. Then this fluid will come out at significantly higher temperature over here. I hope this point is clear. But in this particular case, we call it the surface absorption case, because there's a surface on top which absorbs the sunlight. And we are also calling it conventional solar collector because this is the way all conventional solar collectors are designed as of today. But there are certain limitations over here. The first limitation is on the solar concentration. If the concentration starts becoming higher and higher, this temperature goes up, which is good from a thermodynamics point of view, but from a material point of view, it is not very good, because this coating, the black coating on the top over here that we have put, it is going to deteriorate as a function of the highest temperature. So it is itself having very high temperature. And that is the second disadvantage of this particular design, that the highest temperature, if I take a cross section over here, I draw a line and I want to find out the temperature distribution. You know how the temperature distribution will look like is the highest temperature is at the top, then there is a sudden reduction in temperature over here, then the fluid will have very low temperature over here. And why will it have very high temperature on the top? Because this is where all the absorption is taking place, isn't it? The design mandates that the top surface has the highest temperature. And the biggest problem with that is that whatever is having the highest temperature from that point, it is going to emit proportional to T to the power 4. So that is the black body radiation law. Now, if we compare it with the second design, where we have put these nanoparticles within the fluid itself, so they are flowing along with the fluid itself, we replace the top black surface with a transparent glass surface over here, which means the top surface is again a solid, but instead of being a black coated metal over here, here it is fully transparent glass, which allows the sunlight to pass through it predominantly. So about 90%, 98% of the light would be able to travel over here. And then what really happens is this light electromagnetic wavelength, it interacts with all these nanoparticles present over here. Why is the nanoparticle mandatory in this case? If there were no nanoparticles, the light would just go through glass, then just go through water, because water is fully transparent and come out from the other side. In that case, if I send in cold fluid from here, only the cold fluid will come out. Maybe only 2 degrees temperature rises there, which is what we don't want. We want just like this maximum temperature rise to take place. And the good thing over here is that our collector surface on the top, will not have the highest temperature. The highest temperature over here will somewhere be in the top region, in this region over here. And just compare it with the first case where the collector highest temperature was exactly on the top. So if somebody asks me that why are we so bothered about not having the highest temperature on the top or over here? In this particular case, emission losses will be according to this maximum temperature. But in this particular case, this will, at this point, it will radiate at T max to the power 4, correct? But then it will be reabsorbed in that portion over here also. Some of it will be reabsorbed by glass also. So it is proposed that the efficiency, if we compare in these two cases, it may so happen. So this is the research area that we are currently working in. Then we are seeing under certain simulation and under certain experimental conditions that in some cases, the efficiency for the volumetric absorption, which is containing nanoparticle, is significantly higher than that of the surface-based absorption. And I'd like to present some of those results over here. I want to share them with you. So we look at different type of working fluids. So the main criteria that we have to use this particular fluid is they have to be completely transparent. And the reason for that is, if I go back one slide, if this fluid itself was not transparent, what use will there be if I add certain nanoparticles to it, right? I need a transparent fluid so that the nanoparticles which I add to it, if I'm adding certain nanoparticles, they are the ones which will absorb the sunlight. So that is most critical. So there are a lot of fluids available in nature which are fully transparent. Water is a good example. Of course, gases are a good example, but the gas, the problem is I can't suspend nanoparticles inside a gas. I need some liquid for in order for that to take place. So I think this part I already covered that it need to be. So when we started this particular field of research, we started off with some numerical simulation. So that part I'll go very quickly because this is already well established in the literature long time back. So we created a two-dimensional geometry like this. We had irradiation from the top, and then we looked at the physics behind it. What exactly is, how is light interacting with the, how is the absorption taking place? How is the scattering taking place? How is it that all the energy is absorbed within the fluid? So we looked at concept of scattering. I have talked a little bit. Rayleigh scattering also we looked at. And then we started solving those equations. If you now remember, we already talked about that RTE, the radiative transfer equation. And earlier on, we were having those long terms. And now it looks a little bit different because it is written in the radial coordinates. Earlier, we were dealing it with the Cartesian coordinates. So I'll not go into the details for explaining these equations. So this is the first equation is the RTE. And the second equation, if you're familiar with, is the general equation of heat transfer equation. And this is simply how we have defined the flux. And what we did was we discretized the whole domain into certain finite number of volumes. So this we use the finite difference method. And the objective here was to figure out how would temperature rise take place at each step. And if you follow this particular slide over here, although I'm going a little bit quickly, but one thing you please pay attention to was this last thing over here. So now you can remember we have correlated already that complex refractive index, which was n plus I kappa. So the same calculation, that calculation we are doing, the same principle we have used in this calculation also. So this is the result of that numerical study. So here we were able to show that the blue dots, which represent the uh, result of the numerical simulation showing the thermal efficiency of a nanoparticle based collector, is showing about 10 to 15% improvement compared to an existing surface based absorption design. So these are some promising results, and we wanted to see it experimentally as well. So later on, we published some results where we used different type of nanoparticles in our laboratory, like aluminum, alumina. We used carbon coated also, then cobalt oxide, copper, and we actually used carbon also, amorphous carbon. We found very interesting multi-walled carbon nanotubes, nickel and silver. And because we were just testing it for the benchmarking process, We didn't do it under the flow condition, simple stationary condition we have used. But in reality, in the solar collector, we have to use the flowing condition. But here we just compare two cases over here, like it is shown. The first case was that black surface was on top and we are heating it from a light source from the top. And then the other condition was that we have replaced this black surface with the transparent cover and put different type of nanoparticles whose details are given over here. So two set of experiments we did, one with amorphous carbon, one with multi-walled carbon nanotube. And the results of these experimental study are shown in this slide and the next one. So here I'll discuss because it's shown much more nicely. So this shows the increase in temperature as a function of nanoparticle concentration. So whether we are adding amorphous carbon or we are adding multi-walled carbon nanotube, the more we add these nanoparticles, we are expecting the higher and higher temperature rise we will get, which is true initially. So you can see when we are increasing the nanoparticle concentration, temperature rise is clearly increasing. But what happens when we add too much nanoparticles, and there is a slight decrease in efficiency, which means it's not correct to assume that we should keep on adding nanoparticles. We should stick in that range where the nanoparticle concentration is reached the maximum point. So in this particular case, it's somewhere in this region. Over here, we can say somewhere in this region over here. So with this, what we had done numerically earlier, we have also shown it experimentally, and then we wanted to do it for the flowing condition. So again, we repeated it under stagnation condition 1. So this I'll skip because it kind of shows the similar thing. The only additional thing over here are these IR images. So in addition to having these thermocouples which are present over here, we are having good readings from the thermocouples. We also had IR camera from which we got the readings as well. And currently we are working under the flow condition. So we have created this kind of a spiral collector just for testing purposes and trying to see if we are flowing fluid through it with the help of a syringe pump over here. Then what are the type of temperature rise that we get, both as a function of the concentration of nanoparticle and I think also as a function of mass flow rate as well. So in all these cases, we are seeing significant increase in temperature, which is a promising result. And one additional thing that we went on and did was we wanted to remove or eliminate as much emission losses, because you remember we had talked about from the top surface, there will be some sort of a T max to the power 4. So losses will be proportional to that from the top surface. So we came up with a new concept, and this was proposed by my own PhD student who has then went on and graduated now. So he came up with the concept of putting a layer of silicone oil on top of it. Of course, this works only under this stagnation condition, but I think there can be some geometries under which, under flowing conditions also, we may be able to optimize the design and try and show the similar result over there. So main idea behind it was that if we look at it, even within the nanoparticle based experiment, if we add a thin layer of silicon oil on top, so I hope you are able to see this white portion over here. So there's extra silicon oil which is present over here, which has very interesting characteristic. So we carried out its FTIR analysis, and we found it is very good transparency in the visible spectrum, and at the same time it is having very good absorptance in the IR spectrum where the fluid is going to emit. So this is another way in which we can recapture the emitted radiation, and if it is actually true, we should be able to see an increase in temperature. And this is what we are seeing in this particular graph over here on the top left side. If we focus our attention, so what we are seeing is that if we didn't have silicon oil, then we are having a slightly lower rise in temperature represented by the red curve over here. Compared to when we had the silicon oil, we added little bit of it on top of it, but the rise is little bit modest. So if you see that increase, it's of the order of a few degrees centigrade. This is, of course, the temperature rise is low because our light source is also very modest. So our hypothesis is that if it is done under very high irradiation, then perhaps this delta T, which is correlated to efficiency also, that will show much more improvement. And of course, this was for one particular mass fraction or the nanoparticle concentration, which is mentioned over here. Then we repeated it we wanted to see at different mass fraction, how would the behavior, will it remain the same? So what we found is that in more or less the behavior remains the same. And in all four conditions, whether we add less amount of nanoparticle or more amount of nanoparticle, then we clearly see that adding of the silicon oil leads to an increase in the temperature, which is shown over here on the y-axis, as well as an increase in efficiency. Okay, so I think with this, I will then switch on to the next topic, which is related to water. But before I do that, I just wanted to pause and ask, are there any questions for these particular sections that I have just discussed from the students, or should I go ahead with the water part?
Sir, excuse me, sir. Good
Yes, yes.
afternoon.
Good afternoon.
It is very interesting topic and a very nice presentation by you. Thank you, sir. And I have one question that you have mentioned about this temperature rise in silicon oil, addition of silicon oil.
Yeah.
Can you tell me that is there this is a numerical calculation or experimental data?
This is an experimental result.
Sir, what is the value of solar radiation at this point of time?
Yes, it is experimental, but it is not under the rooftop conditions, which means we are doing under the laboratory conditions. So this is a light source that, can you see my mouse over here?
Yeah.
So the light source is, I think, a halogen lamp that we are using.
Okay. So
it is,
can you, what should be the value of radiation? 1000 watt per meter square or less than that?
in this case, more than that. Because we are able to place, because 1000 watts per meter square is a typical value for sunlight, which is very, very dilute.
Yeah.
So in our laboratory condition, we can actually increase it. Maybe it is, I don't remember the number, but it is at least 5 times or 10 times this. So this could be 5,000 or 10,000.
So if you go for rooftop in outdoor condition, it is very difficult and maybe the result will not come.
Which result?
The temperature rise in outdoor condition as per your experimental setup.
It may not come same to our result, but the qualitative answer will be there. Like if we are seeing an increase in temperature, that increase we will definitely see for rooftop also, isn't it? Value may change, but under one condition, if it is increasing, then under another condition, it will also increase.
Sir, another thing that in the previous slide, you have mentioned that experimental setup for flow of water.
Yes.
First, you have mentioned that in stationary condition, we have experiment and we are adding nanofluid, a nanoparticle along with water. Then our temperature rise is very high. And again, we have tried experiment in flowing fluid. So that is also in outdoor condition or indoor condition with halogen?
I think all the results that I'm presenting today are from the indoor condition. Okay. The reason is in the outdoor condition, we tried it, but it is very difficult to do with this complicated setup right now. In future, we want to do, because everything we have to show, if we want to commercialize it and if we want to patent it, we have to do it under outdoor conditions. But we have not reached that stage today. Yes, we have to reach that one. So we are trying our best for that.
So because the condition you have mentioned that flowing fluid in outdoor condition, it is too difficult. Complexity is there. Yes, in outdoor condition. Yes. And sir, can you say me the mass flow rate of that water, flowing water?
I think it is very, very less. It is like some milliliters per minute or so. It is a miniaturized version of, that is why we are using that syringe pump, you see in our setup.
Yeah, I have seen that. That's why I'm asking that the mass flow rate.
I think it is very less. And you see now here we have that value also. So incident flux, I was telling from memory.
The problem is in outdoor condition when you are using any pump for supplying the water from inlet to outlet, it is the temperature rise is very less.
Yeah. I completely understand, and but our objective was not exactly to show high temperature high. I'll share my slight nuance over here. The objective is, because in our case, we are trying to use a new kind of a design.
Yeah.
So in our case, the absolute temperature rise is not that important as showing the increase in the absolute temperature. Are you getting my point? Because in our case, we are always comparing two technologies. One is the surface based and one is the volume based. So I completely agree with you. Let me finish. I completely agree with you that in rooftop, I will not be able to get this high temperature rise. But that is not upsetting me because of the following reason, that even for surface one, if I put on rooftop, that also will not be higher, isn't it?
Yeah.
So if mine value goes 50% down, that value also will go 50% down.
Exactly.
So what I'm doing is I'm comparing it with that particular case.
Okay.
Yeah,
Sir,
you were saying something.
have you tried any experimental setup with air in indoor condition?
Not with air. The reason is, in our case, we are trying to directly absorb the light, and it's very difficult to have suspension of particles in air.
Okay. Thank you, sir. Thank you, sir.
Thank you. Thank you very for asking very good questions. Are there any other questions?
Sir, maximum efficiency achievable through solar, how much?
Very interesting question. Maybe I'll draw a curve for that one. I have some white space on this slide. So if you can see, actually, answer may be very interesting. It can be very high, 80, 90, 100%, but it will not be of any use because, can you see my slide? So on the y-axis over here is efficiency eta, and the x-axis is delta T. So the curve actually looks something like this. Are you able to see this curve?
Yes.
Yes, sir. Yes, sir. But
Okay. Let me finish answering. Then you will ask follow. Then I am drawing another color curve over here. Let us say a black curve. So I want to give an explanation. This is A and this is B. So what does the y-axis tell? This is the efficiency of the solar collector. What is delta T? How much is the temperature rise? This is not exactly temperature rise, but it indicates the temperature rise in the solar collector. Now the whole competition in the market is for a given delta T. Your question was slightly different. Your question was, what is the maximum possible efficiency? So my answer is it can be very high, 80, 80, 90, 100%. But it will not be of any use. Why? The only point at which it is 80, 90 or 100% is, can you see this point? Here the temperature rise is how much? 0 degrees. So if my solar collector gives minimum temperature rise, it has maximum efficiency. So that maximum efficiency, generally in commercial bidding and other thing, people don't talk about. What they talk about is for a fixed temperature rise, let us say. And why is the temperature rise fixed? Because the end user, let us say he is using process steam or hot water temperature for my cooking, bathing, cleaning purposes. So my end temperature is fixed. On a cold winter morning, my cold water will be 10 degree. I need, under any condition, 60 degree outlet temperature. Then I am looking at two technology. So at the fixed temperature, technology A will have some value over here. Let us say this is 40%. And technology B will have the value over here, 50%. So the only competition is for a given temperature which is having higher efficiency. Can you see this? And then the final statement from my side is, then competitor B will win because he has probably put some better material, better insulation, and most probably his solar collector will be slightly costlier than the solar collector A. It is just like in vehicles. You remember this BS6 norms has come. So any vehicle which is having very high mileage, very high efficiencies, kilometer per liter, usually it is having slightly expensive technology or material inside it. So it's a compromise between the running cost and the capital cost. Yes, please. You had a follow-up?
Thank you, sir. Sir, in solar, can I ask one more question?
Yeah. Quickly.
In solar pond, Any implemented study in India? Anything?
Not that I am aware of. I don't know. I can't answer whether yes or no. A demonstration, small one, I know. Maybe roof again. This just miniaturized version, maybe 2 meter by 2 meter. That people are doing. My question,
Yes,
I think, what you are asking is at the large scale. 100 meter
yes.
or 1 acre level. So I'm
Yes.
sorry, I cannot answer. I'm not aware about it.
Oh, okay, sir. Okay, sir. Instead of salt water, any normal water is not applicable that for a solar pond.
Ideally, it should be normal water, but you remember I mentioned one point. As soon as normal water, you heat and keep it at the bottom. This one solar pond. If your normal water is heated at 90 degree and the top water is at 30 degree, this is unstable equilibrium. So this will come down immediately. This will go up. Whole thing will mix and make it, like how much 60 degree. In order to separate it, either you have to put a physical barrier. The problem with that is then sunlight cannot go through it. Are you able to
Thank
get it? The
you.
only
Yes, sir.
reason the bottom surface is heated is sunlight goes at the bottom and here it is absorbed. Once it is absorbed here, then it will give heat to the immediate molecule surrounding it. That is why the bottom is highest temperature. So in order to keep it down, we have to add salt to it to artificially keep its density high. Okay?
Yes,
I think
okay.
there was one more question somebody wanted to ask. Please go ahead.
Sanjay
Sir, yes, sir. Good afternoon.
Good afternoon.
Very good presentation and very informative, sir. And I studied your concept related to the direct absorption.
Thank you.
And my question is, sir, that much of the studies has been done so far for low temperature application in DSP systems.
Yes.
And it is not much explored in high temperature application, maybe in concentrating type solar collectors. What are the
Yes.
limitations? What are the limitations associated with such type of systems?
Yeah, it's a very good question. That everything, if it is increasing efficiency and temperature, I completely agree. What you have answered, maybe I'll answer in the last slide, because in my summary slide, that is what I have put, that there is huge limitation with nanoparticle. Very briefly, I can tell is the cost is one factor. The second one, agglomeration. That if you leave the system settled, then it agglomerates very fast, because nature doesn't want those small nanoparticles to remain, because it is at a higher energy state. You remember I talked about that example, that water droplet I can break into small pieces, parts.
Yes,
But
sir.
from our example, real life will know that they will come together. If they get a chance, they will start making big particle. The reason why it happens spontaneously from thermodynamics point of view is that this is at a higher energy state, and everything wants to go back to a lower energy state. So there have to, and of course, human being always want to find the challenge of nature and keep it that way. That is why all these 100-story and 200-story buildings are created, because nature want to bring everything down, but human being will create some ways. So it is a challenge. So engineers have to come together. I think a lot of people in chemistry are also working on different type of surfactants on doing it. So there are a lot of challenges. I completely agree. It's a good question.
Right. One more question, sir.
Yeah.
Related to these DSC system, can we integrate these systems in buildings? Because most of these studies nowadays are going on energy efficiency. So can these applications can be augmented with the solar heating or passive heating type systems?
I think so. Anywhere the surface-based conventional system can be used, wherever that part can be used, you are just replacing one feature of that. The end user, if he is getting hot water in his house, he doesn't really know what type of a heater is placed on the top. Just like if I'm driving a car, I don't really know just by driving it that what material the piston cylinder is made of. It's those engineers who have come across it, that earlier they used to made of steel, today it is aluminum, then more material and other development is taking place. Are you getting my point? At the end of the day, user is interested in 2 or 3 things. First thing is, what is the installation cost? Second thing is, I need it for this application. Let us say I need something for cooking, for which I need very hot water or even steam. Now my solar collector is providing very good efficiency, but it is providing me only lukewarm water at 70 degree. So I will not be bothered that, okay, efficiency is better 2-3 times. I am just saying that you have failed my requirement.
Yes, right. Because the temperature rise is sometimes more governing factor. Right.
Exactly. Because if, let us say, a water pulp industry which consumes a lot of electricity to heat water to convert water pulp into paper, for them, if I am supplying a solar collector, he is not bothered if it's a new type of solar collector or an old type. He will be bothered once his basic requirement is met. Once he is assured that, okay, I needed steam at 200 degree, it is giving me steam, then I can impress him that on top of that meeting basic requirement, your old system had an efficiency of 45%. This new one, even though it is more costly, it is having efficiency of 60%. So it's just like that our air conditioning we purchase in market today, B star rating is there, right? I've talked to shopkeeper, every shopkeeper tell consumer is looking at 5-star AC, 4-star AC, 3-star AC, and they want to buy a 5-star AC.
Right, sir. Right, sir. Thank you for your
Okay,
answer.
thank you.
Thank you, sir.
Should I continue?
Yes, sir. Proceed, sir.
So less time I think is remaining, around 10-12 minutes.
Yes, sir.
So
Yes.
and good thing is I have reached the last topic. So I think also be thinking this is 2.5-3 hours. So this is the last part now. So maybe in 12 minutes I'll finish it. Okay. And then maybe a few minutes remaining, I'll take question answer at the end. So this is another very interesting topic which is related to water. And till now, you remember, although I started the talk long time back, we started off with the concept of energy. Even before that, we talked about the challenges faced by our society. Then we looked at energy, whether it is fossil fuel based or renewable energy like solar energy. Then, of course, we went into the fundamentals. We looked at the different applications, radiative transfer equation we looked at. Then we came back and looked at the concept of nanotechnology, how these nanoparticles, they have very interesting properties. They change color at small scale. So we found out that they are having the surface electron properties are the ones which govern the bulk properties of the material. So naturally, their optical, electrical, chemical properties all change at small scale. So we made use of that. I showed some results from my laboratory, some simulation result, some results under the lamp. So all this background, we wanted to extend the work and see, because in India as well as all across the world, and I had shown earlier the challenge faced by society, even in United States, even in India, water is becoming one of the most hotly debated topic. And I wanted to start this topic by providing some background. So I think this part everybody knows, 60%. So this part I will also skip. Some more part I will go into. Yeah, I will start from here. And I think we had talked, some question was there in first session about cooling tower. So I already showed this slide. But it has been observed by scientists and, service provider all across the world, whether it is in US, whether it is in India, that there is a very interconnected web between the water and the energy lifeline and the water energy cycles. So what do I mean by that? For example, if you look at the first statement over here, it says in United States, thermoelectric power plants, which is like the steam power plant, coal, nuclear, whatever, it is the largest single user of water, which consumes half of the water consumed in the country. And this is true for India also, which means in order to produce electricity, we need huge amount of water. And the reason for that, and because of that, what we will see is that most of these power plants which require cooling tower, they are located near reservoirs of water. So I live in Rupnagar, IIT Ropar, and over here very close by there is a Ropar Thermal Power Plant. And in most places in Delhi also Dadri is there and other thermal power plants are there. So we can clearly see there are some natural available water. If not, then some canal is dug artificially, because these cooling towers, you can imagine, they will require huge amount of water cooling. Okay. And interesting part is that most of the electricity which is produced, large portion of it also goes in water treatment and distribution. So what you see over here is an example of municipal water treatment. So water is used for generating electricity, and that electricity we generated, it is actually used for pumping water. So what I just told in words, it is very interestingly shown in this slide over here, which gives a nexus between the water and energy flow diagram. So I like to spend a little bit time on this one, and this I have given the reference is taken from United States Department of Energy. So let us focus on the bottom half of this particular slide. So the blue color portion at the bottom, we will focus first. Let us try and understand what it shows. So it shows on the left hand side different color blocks, dark blue, light blue, then another type of four shades of blue are there. So the left side is the supply side. Then it shows in the form of arrows over here where it is going, for which purpose it is being used, and the thickness of these pipes or blocks over here, flow diagrams over here. Thickness represents the number. So in US units, it is like gallons per day, and we can convert it in maybe liters per day or meter cube per day. So this is essentially volume flow rate. So the biggest thickness of this fresh surface water, it seems is going, like we have seen on the previous slide, it is actually going for thermoelectric cooling. So all the condensers in all the steam fired power plant, they require cooling. Because our mechanical engineer, they remember the TS diagram for a Rankine cycle, right? So this is the TS diagram over here. So we have the turbine, this is the boiler, this is the pump, and this bottom portion over here, yeah, it's small scale, so I can just show over here between from this point to this point. This is the condenser. So we have to dump huge amount of heat in order to condense the steam, which will then again be pumped and go through boiler and change phase, go through the turbine. It's a full cycle. So you can put an arrow over here. It's a small diagram, so I can't show clearly. But that condenser consumes huge amount of water. Some portion it even consumes from the saline surface, right? And very less it consumes from the saline ground and the fresh ground. So these thicknesses we can add together, number we can add together, and let's see what happens out of it. So it is going inside the thermoelectric cooling, it comes out from over here, and then it goes over here, and then it is discharged back to the surface, which means that thermoelectric cooling is one of the biggest drawers of water. It withdraws huge amount of water, but not all of it is consumed. Can you see that one? How much it is consumed? Very small thickness is here. This much is consumed. You will see over here. This is consumed water. And why am I not saying that it is consumed by electrical power plant? Because it is giving it back, isn't it? It is cooling this condenser. Its own temperature increases by maybe 5 degree, 10 degree, 20 degree, whatever is the amount. And then it is heated water, it goes back to the same canal. If it is taken from the saline surface, which ocean surface, it is dumped back same into the ocean discharge, isn't it? You follow this line over here, it goes from here, over here, here, and then it is gone back to the same discharge. But little bit portion is also consumed. So that very small portion, can you see the small thickness over here, this one? This small thickness is consumed. This is consumed water just because of the thermoelectric cooling. And if you go back to that photograph over here, that is probably this particular cooling, that this small amount is going away as clouds. Again, we have already learned that these are the water droplet, purest form of water droplet, maybe transparent, but again, they form an opaque volume, opaque object over here just because of scattering. So that is another thing. And again, same thing we are seeing over here. Although this is slightly dirty water, so a lot of mud effect will be there. So anyway, but then we try and see from the reverse that which is the activity which consumes the maximum amount of water. By the way, all this data is for United States, but if we were to plot the same thing in India, we will get similar looking curve. Only the numbers will change a little bit. So in United States, the activity which consumes maximum amount of water in the whole country is this line over here. And this is coming out of agriculture. So agriculture draws huge amount of water from surface, fresh surface, through rivers, through canals, 80 units. And moreover, it draws so much amount from the ground. So you see this problem in India also is there, that huge amount of reduction in the water level is taking place in the ground. People living near the NCR region, National Capital Region, somebody was saying there are reports that huge, every year some feet of water level drop is there. And it is because it is actually being consumed over here. Some part is of course being discharged. So agriculture also discharges some part through the surface. So there is a lot of runoff from there. Okay. And what about our residential? So we are also consuming at home. So residential over here. So residential we can follow from here. So top part is electricity, but you can see this small pipe going over there, this small portion. So this is the one which is going from fresh water to residential over here. So compare that with the thickness of the thermoelectric cooling and compare that with the thickness of agriculture. This is for the whole country, by the way. It's not just for one city. The whole country, this thickness is, maybe 10 times or 20 times less than that. But this is what we are all in all our homes, even in institute, near classroom, we are all dependent on water. So that is the residential supply for that. So we can clearly see, and on the top portion is for the energy part. So that one you can look over here yourself. But what we are realizing over here, that there is a very interesting interconnect between these two. And this is very interesting. So this is very significant plot. You can just Google it up and look it on the United States Department of Energy website. You just write energy water nexus or the flow diagram, and this is very popular chart given over there. So one or two again introductory thing about water I had, but because of less time is there, maybe quickly I'll go through it. We all know that in March 22 is the World Water Day, and we have seen 2 years back there are already some cities where long lines are actually forming in various countries. This photograph I think is taken from the Cape Town in South Africa, where even day zero was predicted, which means the whole city is run out of water. That will be very, very problematic, and reality issue is there. Then we have to look at, we have understood the problem, what is the solution? So one of the solutions which is there, of course, is the desalination of water, the reuse of water, the water filtration, water purification, all those things is there. And I think over here we are seeing even the capacity in India is actually increasing with time. And what is this country on the bottom, which is having one of the largest installed capacity? This is the Saudi Arabia, UAE, because naturally they don't have any freshwater rivers like in India. Then even US, which is having so much land area, they are investing in desalination. China, Israel is another, Middle Eastern country. Kuwait is there, and of course India is also developing over here. So our investment is increasing in India. So some portion is there about, sewage and other things. So this part I'll skip for now. Yeah. So I want to present some solutions. Okay. So these 2-3 slides I'll skip over here. So in our lab, we are looking at what are the solutions for, cleaning water or desalinating water. So because our expertise already in the heat transfer area, we have two choices for desalination. One is the membrane-based technology, which one I think very common in our household in India, especially if there are students living in hostel. Everybody knows there are a lot of RO units placed even on railway station, bus station, and this is very convenient for small-scale operations where you need maybe 20 liter per day or maybe even 10 liter per day, individual units. But there are some disadvantage with RO as well. So when we want to use at large scale, so maybe thermal is the process where we will look at. And if you look at Saudi Arabia, UAE, most of them, they have installed the thermal process. And within thermal process, the most common one, which is actually being used for last 20, 30 years, is the MSF, which is shown over here, multi-stage flash. But in our group, we are looking at the newer technology, which is the HDH technology, which is short form of humidification and dehumidification. And it is, put it in a simple term, it is simply the water cycle, which is followed in nature, that in the ocean, humidification takes place, air rises, and then once it cools, the air gets dehumidified because it falls down as rain. Then that dry air again gets humidified, and this is a cycle taking place for millions and billions of years on our planet. So we wanted to miniaturize the same thing, and I'll go directly to the results because I'm running out of time. And we wanted to use the concept which we have already explored for solar energy. So you remember we were talking about this solar collector over here. So this part I have already discussed, and this is something which will be the heart of this system. So we are actually trying to build it. And this will be the new part over here, where the humidification, dehumidification takes place in this cycle. Okay. And the main idea is we are supplying the thermal heat through this heat exchanger, and water will, air which is carrying water, once it will be cooled and another time it will be heated, just like in the natural water cycle. So I think, yeah, I'm already past 1 o'clock, so I don't want to rush through it, but I think I don't have time. So I think I'll come to the final slide and then try and summarize. So, in summary, we have looked at a lot of fundamental things, and we have looked at the nanoparticle-based direct absorption collector, how it is designed, how it is compared with conventional collectors. So it is showing some promise, so both numerical and laboratory scale thing. But as one gentleman also asked, that there are certain challenges also. So one is the cost of nanoparticles, then there are studies that even environmental and health impact need to be studied, and there could be some issues with the practical applications where it may coagulate together and then try and sync. So these are some challenges we are still facing in our lab. So it is not near the commercialization stage right now. It needs more work. So we are not disheartened. We are continuing to work in that. And before I formally conclude, I'd like to acknowledge the support we got from these funding agencies. And the most of the work that I have presented is from our research group. There are PhD students, MTech students, BTech, and the JRF scholars as well. So I have included their name, and I'm very grateful to them. And with that, this is my last slide. So I thank you very much. I think we started off at 9 o'clock, I think 9:30. So it has been a 3.5 hour journey. So I hope you will be able to understand. And I'll take some questions now. And the first question was that black body one. So maybe I have to answer it. So I will include it. Thank you very much.
Thank you, sir. It's a nice journey, 3 hours, nice journey.
Thank you. Thank you.
Sir, you clearly explained the solar thermal applications, interesting facts on nanotechnology and color, color identification, and you fantastic interpretation on nanoparticles and their experimental. Now, sir, one question I want to ask you on.
One request I have. I think there is some background noise coming. Can I request
Okay,
all the participants that
I will.
please, yeah, please mute. Other than that person who is asking question, I may request everyone else to please mute. Yes, Dr. Srinivas, please go ahead.
Sir, for emissivity of the surface, most of the calculations I saw, the mathematical models, they are assuming, especially for the surface of glass or others, emissivity, they are assuming constant for radiative to find the radiative heat loss. But is there any, because but that gives more error, is there any mathematical models available as emissivity is a function of temperature, especially to simulate the solar collectors?
Yeah, certain assumptions definitely have to be made. And what we do in our lab is we try and go by the material properties.
Okay.
So for example, different type of nanoparticle, or when we are looking at the different type of coating, so we have to look at the experimental data. So usually emissivity, it does vary. It's a function of so many things. Like
Yes.
heat transfer engineers know that the azimuth angle, spectral quantities, the wavelength, it depends definitely. It depends sometimes even on temperature. Then directional dependence also is there along the azimuth,
Real.
along the zenith. So if we look at it in reality, but what is the good thing is that even though particle may be nano, our overall energy balance we are doing, I think, at the macro level.
Yes.
So we can assume all the directional thing, we can assume it is isotropic. So the only variation we look at is significantly is with wavelength and little bit with temperature, because for material property, I think 100-degree increase in temperature, it doesn't change that much.
Yes.
But in wavelength, if it even goes from 1 micron to 1.2 micron, there is a drastic change. So wavelength is the main thing. And
Okay.
those data is available. I was showing that data from Brewster book, that Excel sheet is there. So, and there are so many books which show this material property. So anyone we can use. Yes, yes.
Sir, in the one more small in nanofluids, you mentioned is the base fluid indicates the is it indicates only liquid or it also includes the gas?
In principle, it can be any fluid. The
Any
only
fluid?
issue is that with gas, all these particles, like we are using carbon particle, aluminum particle, in our experience, it's difficult to keep them suspended in air or in gas.
Okay.
Unless that gas is continuously moving with huge amount of turbulence and it is providing some lift automatically.
Most of the cases, I think liquid. I think.
Yes, yes, I am certain. I've never seen a published paper where the gases are used. Although there are some, where although I would correct myself, where this pulverized, even in
Yeah.
the
Coal.
this power plant, yeah, they use a pulverized coal and then it is just blown away by the air which is going in. But I'm not 100% sure whether they are looking at the radiative transport properties over there. So in principle, it is possible that even gas can carry around the pulverized particles.
Sir, from participant side, there are few questions. May I read from chat box?
Yes, yes, yes. Please, please.
Uh, One question from Dr. Piyush Kumar. Is there any less costly equipment to measure the thermal conductivity of nanofluid? He's asking about the equipment, thermal conductivity equipment for the nanoparticles. I think
Yeah, I think there are some
low
standard
cost.
equipments, but
Uh,
are there even low cost to that? I'm sorry, I don't know. Whatever is the standard, that is the one we use.
uh, one minute, sir. Is there any questions from participants? Sir? Directly, we may interact.
Yeah,
Through.
if I'll take one opportunity, because I think one gentleman is waiting for a long time. I think
Yes.
he was
Okay.
perhaps the first one to ask question, and I haven't answered it. I was remembering there would be some slide in which emissivity would come, but
Yeah.
it didn't come. So maybe I'll just answer it verbally. There is no slide
Okay.
for that. So verbal, the answer is yes. It seems like a misnomer that black body is supposed to be a body which appears black. Why? Because it is a perfect absorber. If only this thing was true, then sun should appear black. But there are two laws in nature. The second law is that any body which exists, any object which exists in our universe, in our nature, it has to have a certain temperature. Even if it is 2 Kelvin or 5 Kelvin, or let us say at room temperature, it is around 300 Kelvin, then the nature behave in such way that every material, every atom has to emit the thermal radiation. And this comes from that quantum thing, and I think Max Planck is given the credit for it. He came up with that theory, Planck's law of this emissive power. Now the only thing in nature is said that yes, every object has to emit, but it has only put a upper limit, which means if we are little bit interested in heat transfer, just like black body, there are gray bodies also. So gray body is something which has a emissivity not equal to 1, but little bit less than 1. Let us say 0.8. It has a constant value almost at all wavelengths. So if let us say some object has a emissivity of 0.3, so that will be a special type of a gray body which emits 30% of a black body at a particular wavelength. So that I can draw with a diagram over here, I think. So for black body radiation, according to Planck's theory, is something like this. This is at a particular temperature, let us say just at T1. And if this is a black body spectrum, then that gray body which I was talking about, which had a emissivity of zero point 0.3, at each of these points, it will emit 30% of that at each of these points. And then I join those dots. So this is also at the same temperature, T1. So nature allows this difference. What nature doesn't allow is another body which is at the same temperature. Let me draw in green color. it is also at temperature T1, and then this is also allowed that it can go up and down, it can go very low, it can go like this. But if I draw it in black color, so the only thing which nature prohibits is it cannot be like this. Because this portion is actually violating that Planck's law. And this, I'm making the assumption that all of these four bodies are at the same temperature. So Planck says that if there is a black body, there cannot be any body which is having a higher emissivity than that black body, which means, in other words, he's saying that emissivity maximum limit is less than equal to 1. So this point is clear from the emission point of view, which means if, let us say, I have a black body in my room, and it's very easy to create black body also, and in my room its temperature is 300 Kelvin because it is sitting with me in my room, then that black body will completely appear black, no doubt about it. Why? Because it is emitting. But you remember that lambda T max rule was that this is about 3000 micron Kelvin. So it is emitting at a wavelength of, its maximum wavelength is 10 microns, which my eyes cannot see. So my eyes will not tell me the whole story from here to here. Eye is not a perfect detector. Eye is only detecting in this wavelength, 0.4 micron to 0.7 micron. So what I as a human being call black and you as a human being call black may not appear black to say there are some snakes, rattlesnake and other snakes, which actually can see in this wavelength. And the reason they can see is they want to catch the rat at night time, squirrel and rat will have this particular temperature. It is emitting. Just like our police force and army force, they will use the night vision goggle. So my dear friends, if we use night vision goggle and look at this particular thing, just like at our IR camera, some image I have shown, it will not appear black indirectly. So there is no link of the black body having to appear black when it is having a particular emission. So that is my answer. Have I answered the question which was originally asked?
Yes, sir. Yes, sir. Thank you, sir. Kindly switch on your video so that we can take a photograph. It will be
Yeah, I
memorable.
tried many
I
times.
requested.
I asked, look, you have to help me. I'm sharing my screen. But here you see this button.
Sir, you may yes, yes.
Then how will it come? I have another technique, we can always think of new technology. So here you can take. Are you seeing this one?
Okay, sir.
Is it okay? Or should we find another way? In Google Meet, I can appear because Google Meet, it does not create blank.
Okay.
Or I can appear on this WhatsApp video. If you want a photo for some documentation, WhatsApp video, I think I can come.
Sir, great interactive session and almost 3 hours gone. People are not bored at all. That is very interactive.
Thank you very much. Thank
Lot
you.
of learning, practical experience. Oh,
I just hope
Sir,
that they are drinking a
sir,
lot of
little.
tea. Yes, yes.
Okay,
Sir,
sir.
sir, may I little small question, sir?
Okay.
Yeah, with permission of Dr. Srinivas,
Yeah,
because he is
yeah, sure, Doctor Saab. Doctor
No,
uh,
no,
Saab,
sir. Proceed, sir.
Dr.
Okay.
Srinivas is moderating.
yeah, Doctor Saab, kindly permit.
Okay, sir. Proceed.
Only little, sir. We are supposed to take certain new ideas for the prototype development, incubation stage pay. Sir, can you share some tips on the new things? Some tips?
I think, yeah, I remember you had asked question after the first session, and I
Yeah.
had mentioned that I'll share a lot of new information. So I think if you attended this second session, you would
I
find
was
I have given so many new
okay.
ideas. So I
Okay,
think all
okay.
of them are the tips from my side. You feel free, you can write any of
Okay, okay. We can communicate also later on, sir.
Absolutely. My email is given over there. The only
Right.
problem I face today is somehow I am not able to switch on my video. If I could do that, I think that would be great. But
Right, sir.
you can get my email is available to everyone. Thank you.
Yes,
Thank
yes.
you.
Right, sir. Thank you. Thank you very much, sir.
Yes, sir.
Thank
Thank you,
you.
sir. Thank you.
Okay.
Thank you, sir. Thank you.
Thank you, sir. Thanks a lot.
Okay. Thank you very much. Thank you.
Thank you, sir. Bye, sir.
Okay. I'll disconnect now, Dr. Srinivas.
Yes, yes,
Thank
sir.
you.
Bye, sir. Thank you. Thank you very much.
Okay. Bye bye.
Dear participants, today after lunch, 2:30 we have class. That's around. That is lecture is on harmony in the family values in human to human relationship by Dr. Rajpreet Kaur, Punjab Technical University.